Hello. So, welcome back from your break. I'd like to introduce some friends I've got from ASOS. Now, for those that don't know, ASOS are a key sponsor of the Data Science Festival, and their talks are always amazing. So it's no surprise that we're literally as full as we can possibly be. And I think you probably hit the mark with your talk title. So we have Thomas Buffagni, Priscilla Fearn, and Eduardo Nigri from ASOS. They're going to be talking about AI demand forecasting. Eduardo is an experienced data scientist and machine learning engineer with a track record in applying machine learning to a wide range of domains, including retail, finance, medical imaging, and mobile networks. He's currently working at ASOS as a machine learning scientist to deliver business value through demand forecasting for stock replenishment. Eduardo? Which one's Eduardo? Eduardo. Hello, Eduardo. Priscilla is an AI product manager who brings a unique blend of experience to the table with over a decade of success in commercial environments, where she excelled as a retail manager. Leveraging this extensive background, she now channels her expertise into the dynamic realm of AI, where she is driving transformative changes, bringing cutting-edge and impactful products to life. Say hi, Priscilla. Thomas is an experienced machine learning engineer working with the AI forecasting team at ASOS. With experience in startups and larger companies, he specializes in deploying machine learning and deep learning models to production to build safe and reliable AI products. Okay. But they're three really good intros, by the way. I want to give you all a job just based on that. So, okay, round of applause for ASOS.
Thank you, guys. Well, welcome, and thank you for being here. Today we'll be guiding you through the journey that led to this moment, a success story clearly resonating with a lot of you. But before we start, let us introduce ourselves. And I'm Priscilla, I'm a product manager, as you've heard, and part of this cross-functional team. And I'll be the one starting the session, giving you an overview of the challenges that we faced when building our forecasting model.
Hi, everyone. My name is Eduardo. I am a machine learning scientist at the AI forecasting team. And I'm going to be talking a little bit about the modeling challenges that we had, how we solved them, and some of the insights we had.
Hi, everyone. I hope this works. Yes. So yeah, I'm Thomas, a machine learning engineer in the AI forecasting team, and today I'll be talking about the challenges we faced when deploying those models to production.
Great. So we are a cross-functional team, like most of the AI teams at ASOS, made up of product, science, and engineering, which means that internally we have all the skills and knowledge required to build AI solution end-to-end, minimizing dependencies on other teams, other departments, and also allowing us to iterate faster. So we are ASOS. Some of you may know we are a global e-commerce platform dedicated to fashion-loving 20-something around the world, with over 25 million active customers, reported revenues over £3.5 billion, and operating in more than 200 markets. We make fashion available and exhilarating around the world. At the heart of our platform lies AI, driving essential functionalities like the recommendation systems, pricing engine, personalized search, and of course the AI demand forecasting model, which we'll delve into today, giving the business the ability to anticipate the demand of our customers for their favorite products and make sure that they're available on the platform when customers want it. It is important to note that most of our AI systems are built in-house with the overarching goal of serving our customers, but also bringing value to the business and its operations. But why are we here today, and why is forecasting important? It is a crucial aspect of business planning and operations in businesses across various industries. It also serves different purposes. Just listing a few examples here. One of them is production planning. Anticipate how many units and what will be demanded so you can start production on time. In supply chain management, anticipating how fast will something be selling to deciding where to put it into your warehouse. Financial planning for budgeting or revenue forecasting. This is really just to name a few. In our case, what we worked on was demand forecasting for inventory management. So notice here the word demand, because what you're forecasting for is not always necessarily demand. In the last example that I highlighted was financial planning and revenue projection. What you're forecasting for is not demand, but it's sales. How much revenue is going to be coming back into the business? How much sales can I be expecting? So in demand forecasting for inventory management, what businesses need to do is anticipate future demand to plan accordingly. In this specific example, which was our case, the operational teams were merchandisers in charge of buying. And what they needed to know at any point in time was, today, what is demand going to be like in a week, in 2 weeks, and many weeks into the future, to make sure that they bought enough stock so that when customers want to place the order, when their demand arises, it's available in the warehouse. They can click a button and get it shipped. Buying the right amount means not buying too little and running the risk of being out of stock, but it also means not buying too much and running into excess inventory and all of the costs associated to it. This is obviously a very simplified example, so let's look into why this is in practice a much more complex problem space. You're working with multiple operational teams, and by multiple operational teams, we don't mean this, but it's rather something that looks like that. Having multiple requirements. So in our case, we worked on demand forecasting for continuous products. Continuous products are those that are ideally continuously available, the products that our customers have grown to expect and depend on our platform. They're the ones that have been selling for months, if not years, so different from those that are more trend-led and have more of a short history, which means that we were working with hundreds of different merchandisers, forecasting for tens of thousands of products at each individual size and per location, making this hundreds of thousands of different forecasts. These different operational teams also had different requirements or different responsibilities. So some are in charge of buying or replenishing finished goods that come from a local supplier. An example of this would be a lipstick, which only takes a few weeks to come back into the warehouse, which means that what they wanted to know is what the demand was going to be like in the next few weeks, couple weeks. While other teams were responsible of ordering some finished products, but that may come from further away, maybe by ship, and needed to know what the demand was going to be like in 3 months, 6 months, or plus. While other merchandisers wanted to know what the demand was going to be like in a year into the future or more, to be able to make sure that the factory had enough raw material to produce something that they'll be placing a reorder for. These different teams having different responsibility also meant that they had different workflows and manual processes that obviously can't be ignored and needed to be accounted for. Sounds like a complex environment, but it doesn't end here. Finally, there is the crucial aspect of adoption. Please raise your hand if you've ever built something with a purpose that is no longer being used or was not used much. Okay, I appreciate the honesty in the room. So, AI and machine learning are intricate domains, and your user operational teams you'd be forecasting for may not necessarily be knowledgeable about it, and sometimes may not even be comfortable about it. Working. How do you make sure that they understand it enough or trust it that they actually want to use it? Then there is change management. Any sort of AI and automation brings the inevitable change in processes and change management. Imagine you've been doing your role for 5, 10 years or plus, and an AI expert comes and tells you that you need to change the way you're doing things. And finally, you've launched something, you've landed it, people are using it. How do you make sure you keep continuous retention so that your business can continue bringing impact, or what you build continue brings impact? This is where Eduardo will step in stage and tell us how we've solved for some of these challenges.
Thank you, Priscilla. All right, so as you just mentioned, one of the challenges that we had is that we needed to provide hundreds of thousands of forecasts. So we did an approach which was not only accurate, but also scalable. We experimented with some of the common approaches for forecasting, for example, exponential smoothing, ARIMA, linear regression. But in the end, we found that the best approach for us was the light GBM, for being not only accurate and scalable, but also reasonably explainable, which is really helpful to understand why the model is making the predictions it is making, and also to explain to your stakeholders the predictions. And in terms of the features we use in the model, here, just in a nutshell, we have three main types of features. The first one is based on previous sales. So we have, for example, the average sales for the past year. The second type are based on product attributes. So you can have, for example, the product category and the product price. And the third one were based on calendar features. So for example, you can take the season you are forecasting for. But then another challenge that we had is because we have multiple teams which have multiple requirements, we needed to forecast into several weeks into the future on a weekly basis. And Light GBM cannot be used to doing that out of the box. This is called multi-step forecasting. So once again, we did experiments using different approaches. And in the end, we found that the one who worked the best for us is what is called a direct multi-step forecasting. And this is quite simple. You have one model for each horizon you are trying to predict. And then you're going to train your models independently. So let's take one example when you need to forecast the next 5 weeks. In this case, you're going to have one model for each one of the horizons you are forecasting. You're going to train them one by one, and then you use them one by one as well to make your predictions. So this is great, but before we think about how we're going to train our model, we need to figure out what is the right data to feed into our training. And so, as Priscilla said, when you are forecasting for inventory management, it is really important that you forecast for the demand instead of the sales. And the difference between the two is that you can only sell when you have stock, so the sales depend on the stock you hold, whereas the demand will exist regardless of how much stock you hold. So let's illustrate this with one example for a shirt. Let's imagine that the demand for this shirt is as shown here in this plot, where here on the horizontal axis we have the time in weeks, and on the vertical axis we have the units. So let's now imagine that the stock position for this shirt is as shown here in this plot, where we have the number of units available in stock at the end of each week. So if you look here at the stock data, you might realize that for some of the weeks, the stock was 0. So this means that the product was out of stock. And as a result, when we look at our sales data, it might look like something like this, where we have 0 sales when there's no stock, or lower than usual sales. And that is because the stock can end during the week, or the new stock can also arrive during the week. So you're going to have lower than usual sales. So it is really important to address this in your model or in your data. Otherwise, your model is going to learn to predict low or no demand when there is no stock. And this is going to be true even if you don't have the stock information as an input to your model, which, by the way, is not usually a great idea. So once again, there are a couple of approaches you can try in this case. For example, you can try to input your demand when you don't have stock. And we ran some experiments. In the end, we found that the best approach for us was to simply remove the out-of-stock weeks from our model features and targets. So this means we never train our model to predict weeks in which there was no stock, and we also don't evaluate our model in those weeks. And for the features, all of our features which are based on previous sales, they will exclude any weeks in which there was no stock. And once we made those changes, we found that the model was not only more accurate overall, but it was also less likely to underpredict. And this is precisely because our model was no longer learning from data of sales, which were not representative of the demand. So in speaking of underprediction, as we talked before, when you are forecasting for inventory management, there are very different risks associated with under and over forecasting. When you under forecast, then you're going to buy not enough units, and you're going to go out of stock, which, of course, you're going to miss sales in this case. Whereas if you overpredict, then you're going to buy too many units, and you're going to overstock, which also has associated costs and just wasting space in your warehouse. So because those two situations are quite different from one another, it's very likely that they're going to have very different costs for each business. So it really depends on how much you want to avoid one compared to the other. In our case, we wanted to avoid overstocking, but we also really wanted to avoid going out of stock, because this meant that our customers would not be able to find the products they want from our website. OK, so now how do we solve this problem, considering that most of the commonly used regression loss functions, they are invariant to whether you are under forecasting or over forecasting. So let's illustrate this with the mean absolute error, or MAE for short. And in this loss function, you are simply taking the absolute value of the difference between your forecasted value y hat and your target y. So to illustrate how this function is symmetric to the direction of the error, we can use this visualization. Here we have on the plot, on the horizontal axis, we have the error of your model, and on the vertical axis, we have the penalty you are adding to your loss function. So this means that if your error is -1, which means that your forecast is 1 unit lower than your target, then you're going to add a penalty of 1 to your loss function. Whereas if your error is 1, meaning 1 unit above your target, you're going to add a penalty of 1. So you can see how this is symmetric. So now how can we incorporate this requirement into our loss function that those errors should be penalized differently? And so one solution for this is what is called a quantile loss, which has one extra parameter called Q, and that can take values between 0 and 1, and then you can use this parameter to decide how much you want to penalize one error more than the other. So to explain this loss function, here in this first line, we have if you under forecast, then you're going to penalize your prediction by Q, whereas in the second line, we have here that if you over forecast, they're going to penalize by 1 minus Q. And once again, we can use the same visualization to illustrate how this works in practice. If you choose a value for Q of 0.5, I think you can probably see from the equation that this is going to end up with a symmetric loss function once again, which is very similar to the MAE. However, if you choose a lower value for Q, such as 0.3, then you're going to apply a lower penalty when you underpredict and a higher penalty when you overpredict. Whereas if you do the opposite, if you choose a higher value for Q, such as 0.7, then you're going to apply a higher penalty when you underpredict and a lower penalty when you overpredict. So in our case, because we wanted to avoid going out of stock more than overstocking, then we needed to choose a value for Q higher than 0.5. And in practice, we found that the choice of this value can be done through experimentation by seeing how much under and over prediction you get for different values. And also getting feedback from your stakeholders is also very helpful to make this decision. Which brings me to a very important point about how to effectively communicate with your stakeholders so they can learn to understand the model and so they can trust it. This is very important in terms of adoption, so it's really a critical step. So firstly, it's very important to explain to your stakeholders how AI and machine learning models work, and also to adjust the level of technical detail depending on who you are talking to, and allow them to clarify any misconceptions they might have about AI. Second, it's really important to have regular catch-ups with them to make sure they understand that this is an iterative process of continuously improving your model, and also to manage their expectations in terms of timelines and model performance, especially because some people might think that AI will work like magic. And thirdly, it's really important to get feedback from your stakeholders about your model predictions, because this will make sure that they are being heard, their concerns are being addressed, and also to identify which areas you need to improve your model the most. So this is all great. I talked a lot about how to create those forecasting models, but then now it begs the question of how can we make this a reality with both speed and robustness? And so to answer this question, I'm going to pass on to Thomas, who's going to explain how to scale up your feature engineering.
Thank you, Eduardo. So, as most data science project, we started our feature engineering with pandas. It's a very popular library in the data science community. However, as we scaled up our data set, moving out of our POC phase, we scaled up to around 100,000 time series, one for each size of each product in each warehouse. So we quickly ran into scalability issues. We needed to migrate to PySpark. So PySpark is the Python interface of Apache Spark, which is a distributed processing system designed for big data workloads. So we onboarded data engineers to our team. Everyone else had to go through a learning phase. It took quite a lot of time and a lot of efforts, but it all paid off in the end. Because if we look at this bar chart with a lot of information on it, the red bar corresponds to the runtime of our feature engineering written in pandas, and the green one represents the runtime of the feature engineering written in PySpark. We achieved a 10x speed up, which was huge for us. We were very happy about it, and so I want to show you what our final setup looks like to achieve this. So all of our PySpark jobs run on Databricks, whether it is data ingestion to get the raw data in a place that we own, or feature processing to extract as much information as possible from the data. And our model training and serving run on Azure Machine Learning. Azure is the cloud of choice at ASOS, and AML is their machine learning service that provides different services, both to build batch machine learning models as well as real-time models. Thankfully, we can unify these two components under the umbrella of Azure Data Factory, which is their managed data integration service that combines multiple data sources as well as multiple compute in a single solution. And additionally, we automatically deploy this infrastructure using Terraform because we found it easy to write reusable Terraform modules that can be shared across projects and even across teams to accelerate the deployments of our models to production. Nice. Now we've made our pipeline scalable. How can we make sure that we can iterate quickly? Because we are all used to Jupyter notebooks. Once we make our system more complex, it's more difficult to experiment and to update it. So in our team, we made the decision to make each step of our pipeline executable as a standalone component and to save each intermediate results so we don't have to run the whole pipeline over and over again during experiments. So let's take an example. A scientist in the team has a brilliant idea and they want to improve the model training. They're able to isolate the model training step in our pipeline, update it as they wish, and run it on a remote compute cluster with a single command. Once they are done experimenting, very little engineering work is needed to update our production pipeline because they were directly modifying production code during experimentations. All right, we've seen both the scalability aspect and the flexibility aspect of our pipelines. But now, how can we make sure that our forecast is actually adopted by our users? It's an essential part of a machine learning project, and Priscilla, the other engineers, and myself, we spent quite a lot of time trying to solve this. So, as Priscilla said, we have quite a lot of users. But thankfully, they all use the same tool, Microsoft Excel. So they spent a lot of time importing the data and processing it in Microsoft Excel. So we figured that we could actually generate those files for them with Python, saving them both time and providing a more accurate forecast. However, in reality, it looks more like this. They all have their own ways of using Excel. As we explained at the beginning, each team is responsible for different types of products, which means they design their Excel files to satisfy their respective suppliers' requirements. So it was a bit more difficult than we thought. So we embarked on a long journey of discussions to understand their needs and to consolidate them into a single universal format. And I have to say, they actually love it. I promise you this comes from actual feedback and is not made up. Okay, the names are made up, but the feedback is real. However, we're not done yet. We have created a final product that can be used by our users. However, even if we don't make any more changes to our pipelines, there's one thing that is constantly evolving, the input data, which is why we need to implement safety mechanisms because, for example, a drift in the data distribution could impact the performance of our models. So let's start with data validation. For data validation, we use PyDQ, which is a framework developed by AWS that relies on PySpark to measure data quality in large data sets. So for example, we track different metrics such as the number of unique products, or we check for missing data to make sure our model are trained on the highest quality data as possible. Additionally, we monitor our performance constantly with a Grafana dashboard, which provides different levels of granularity, such as the global performance over time to detect potential degradation of our predictions. But we are also interested in team-level metrics to provide each team with the best forecast possible. The problem here is that, as we said, there's a lot of them, approximately around 100, and we cannot track all of them manually in a single dashboard. So we had to complement this solution with an alerting system based on Azure Monitor that can alert us when important metrics cross certain thresholds, for example, so we can take action quickly. And despite our best efforts to keep everything under control, we are not immune to unexpected changes in the data or new requests from our users. Every week, we generate around 1,000 Excel files, and the opportunities for something to go sideways are limitless. which is why we integrated our solution with ServiceNow. ServiceNow is widely used at ASOS to help us with the development of digital products. It is the single point of contact between our team and our users. More specifically, we use a support ticket system to help our users raise any issues they might have with our solution. And we can track different metrics about them, such as the number of tickets we get per month, or how long it takes us to solve a ticket on average. And additionally, we developed our own internal forecast analysis tools to help us answer their questions as quickly as possible.
Great. Thank you, Thomas. Thank you, Eduardo. As you guys can see, we didn't start the journey with the product that we have today. It's been, a series of iterations, learning along the way. But what we were hoping with, today is to share our experience, and so that if any one of you guys is about to embark on a similar journey, you're now better equipped to do that. Thank you very much for your attention, guys.
Okay. Any questions for Thomas, Priscilla, or Eduardo? Lots of questions. Do you want to do that slide first? All right, we're going to need to throw the mic. Thank you.
Je l'enlève et on partage.
Your hands over here. Maybe you first, because you're nearest. That's very good.
Hi there, thank you for a wonderful talk. Given that this is such an iterative process, if you had any examples of drastic over forecasting, how did you resolve them?
Sorry, what was the word you said?
Given that this is an iterative process, if at the start you had examples where the forecast was actually over forecasting for demand upon reflection later, how did you resolve it later?
Yes. So what usually happens, and Thomas talked about our support system, they usually will give us some feedback on the forecast, and what we do is we usually look at the specific forecast that was made, and we choose like SHAP, for example, to look at what happened to the forecast. It's also really important to look at the context. For example, take the past year of data, stocks, and all of that kind of information, because with this you can have an image of why the forecast was that way. For example, if it was over forecasting, sometimes you might see that there was a peak in sales for that product very recently, and then it was out of stock. So the only demand information you have was on that week, for example.
Hello. Yeah, thank you so much for the insightful talk. I have two questions. The first question is, how flexible are the variables in your forecasting models? For example, when it comes to weather or seasonality, we know that weather changes as well, and we had a relatively mild winter, so people might buy less of winter clothing. How do you adjust that? Do you have a average for the past 5 years, or how do you do that?
So we don't have weather features in our model, but we have seasonal features. For example, what is as I mentioned, what is the seasonal forecasting or the month? And we find that just because we have so many products of each season, that this is enough information to forecast. But also we find that some of the products, they can have tags, like this is a winter product, this is a summer product, and this also helps a lot. So yeah, we don't have any weather features because we find that the information from the previous sales for each season is enough in that case.
Awesome, thank you. The second question is, how do you deal with fast fashion concerns? Do you actually create artificial demand just to influence how consumers behave in terms of how fast, the turnover they buy things, the same user buying the same a lot of things within a short period of time? How do you deal with that kind of aspect?
Yeah, so the model we're talking about today is mainly used for continuous products. So those are products that they stay months or years in the website. So we don't tend to have those problems because we already have some history of the sales. But actually, we are actually developing internally another model for those cases because the forecast will be very different. You don't have as much sales information to rely on. You have to use other things like product attributes, for example.
Awesome, thank you so much.
Hi. Hi, over here. First of all, thank you for the presentation. I just had a quick question about your tech stack. So I saw that you're integrating Databricks and Azure ML under the umbrella of Azure Data Factory. So my question is that what is the advantage of using Databricks instead of, for example, Synapse for your processing of the data using PySpark?
Yeah, so
So I have to say, we had a lot of Databricks set up already because of our data engineering teams. So it was very easy for us to migrate to Databricks rather than using a different AML service, because we had already some Terraform modules developed, as I said, or some setup to like just plug in a script, and you can use the infrastructure very easily. And we had some experiences with Synapse in other teams, but because our experience with it was not as big, we had more struggles to just integrate everything together. So yeah, that's mostly why we use Databricks right now.
Is there any advantages identified for Databricks over Synapse, or not really?
I have to say, I could ask the people that are sitting there because they worked with Synapse and not me, but no, not
The
you.
guys with the ASOS.
Yeah, so Eduardo, thanks very much for showing the loss function. I was just curious with the forecasting side of things, because I guess you said over forecasting is worse than under forecasting. How do you do that calculation in terms of, I guess, the missed opportunity value for not having the item in stock? Because I guess when you've over forecasted, you get the timeline, you've got cash tied up in, well, you potentially will have cash tied up in the stock, and you've got to pay the suppliers back before the payment terms sort of lapse. But how do you work out that missed opportunity value?
Mm-hmm. Yeah, so in our case, actually, the under-forecasting is a worse problem. But in terms of measuring the costs, this is a very complex problem because there are a lot of steps when you're providing the forecast. Because then, for example, you have the supplier, if they can actually fulfill or not. You have how much budget they have for each product type. So it is really hard to get a cost on each one of the errors. So what we do is we generate our forecasts and get feedback from our stakeholders. And because they understand so well their products, they are able to say if the forecast is looking good or not, if it's too high or too low. And we, of course, we have the metrics as well to look at as well as the feedback. Yeah.
Hello. Hi. First of all, thank you so much for your talk. It was very insightful. My question is, how do you get in all of your different data? Because like obviously you've got like third-party like merchandisers, and you might have like a red dress. And for you, ASOS, this has one ID, but then the merchandiser might have a different ID for it. Like, how do you organize all of that to make sure that you're actually tracking all of your items and all of your sales correctly?
So first thing is that when we started this project, there was a lot of time spent to understand what the data is on the merchandiser side, so we can make sure we use the same identifiers for sure. We had some learnings along the way because some IDs might change or like events might happen. So there are different, we had to combine data from different sources, which was a big part of the data engineering work, to match IDs, merchandising IDs with actual products, because, yeah, as I said, some IDs might change, and in a real world, like the data can be messy sometimes. So, yeah, it was a big engineering work to spend some time with them and understand how they use their own data so we can try to match their process. Yeah.
Hey, hello. Yeah, thank you for the talk. I have a question around your target variable, because you had a very tricky problem where you want to forecast demand, but you only have sales. So how do you take into account returns in your forecasting of demand?
How to take out the returns? Yeah, so here in this case, we are forecasting only the demand, and the returns are forecasted separately. And at the moment, we don't have a model for that yet. We are developing a model in-house just for the returns, but we keep them separate just to make it the problems a bit easier. But then in the end, when we want to calculate how many units to buy, then we take both into account.
Hello. Hi. Thank you for your presentation. I have one question for each one of you, just short questions. So for Eduardo, I wanted to know what kind of features are being used by your light GBM model. And then for Thomas, what does the forecast analysis tools consist of at the very end of the pipeline? And for Priscilla, now that you have built what looks like robust pipeline, how do you keep improving it? And what are the next steps in your product pipeline? Thank you.
Yeah, so on the features, if we take all of the features we have, we can broadly categorize them into the 3 types that I showed. We find that the most relevant ones are usually based on sales, the sales from the previous weeks when we remove the out of stock. And what we find is, which is very intuitive, because we're predicting several horizons, the shorter horizon, so the near future, relies more on the recent history of the sales. For example, the last 3, 6, 9 weeks, whereas the forecast, which is more long-term, let's say a year, they will use a longer period in the past, precisely because the more recent demand information is going to be super relevant for the next few weeks, but when you're looking so far into the future, it's not so relevant anymore. So yeah, that's one example of the ones that we find are the most relevant in most of the models.
So regarding the forecast analysis tools, at the moment, they're mainly Jupyter notebooks with different functions to analyze the code that we found our stakeholders had a lot of question about. So we can provide different metrics very quickly because, as we said, there's like around 100 teams in total. I think it's around 300 people. And independently, they get similar questions. So it was quite easy to identify some use cases where we could provide an answer quickly to them. And maybe Eduardo has some stuff to add about that. But
yeah, mostly we just automate so we can easily get the predictions from where we save them, just check everything, sometimes we need to get the features from a different place, and then we can generate some plots showing everything we need, showing the past sales, past stock, all the future forecasts, showing which season is which, because it's very important if you're forecasting for summer or spring, for example. And then, yeah, we can just do with one function, you call it, and then you get all the diagnosis of the forecast.
And for the last question that was linked to continuous improvements, initially we spent a lot of time with those regular catch-ups that Eduardo talked about. But as the product matures, we're relying more and more on ServiceNow. But I have an example of something that was, came from user feedback that was a good pointer for us to work on. But some user raised that the forecast of some of the products looked too flat. And we looked into it, and the guys integrated LMs so that we would be able to read the product description and further understand if something is very, very seasonal. Like if there's a word thermal in thermal tights, it's very wintry. So any feedback that we get is often very valuable. Sometimes it's a minor change, and some others is the integration of LLMs. But it's really continuing to listen to the user, their expertise, to improve what we're bringing to the business.
Okay. Yeah, thanks for the talk. I have a couple of questions. The first is regarding the use of the loss function.
Sorry, could we just keep it to one because
okay.
time is really short.
Okay.
Sorry.
Sure. Loss function, I noticed you've used the quantile rather than the other one. What's the advantage? And do you use sentiment analysis as well?
Sorry, what was the other one?
Sentiment analysis.
Okay.
Yeah.
Yeah, we have been using quantile loss precisely because we have this thing where one type of error is different from the other. I'm not super familiar with sentiment analysis, how it can be used in this case. But yeah, it was just a very natural choice for us because we started with a loss function such as the MAE or the MSE, and then once we realized that we had to penalize one error more than the other, then we went to the other one. But yeah, I have not tried sentiment analysis, this one.
Sorry, we've got time for one more question. I'm sorry, we have to finish on time so people can move between rooms. Sorry, that gentleman there. Thank you.
Thanks for the presentation. It sounded like you're only training your model on first-party data. Is there any reason why you're not using third-party? I'm thinking like second-hand clothes sales, which are picking up.
Yeah, so we found that because those are continuous products, we have so many products and so many sizes and different locations that the data was enough to produce a really good forecast. And because we use an iterative process, we like to start iterating quickly and try to get the results as soon as possible because this is what brings value to the business. So that's why we have not explored any third-party data yet. But with other models that we have, for example, the one I mentioned that we're developing for more fashion products, this one we're looking at more external data that can be used to make the prediction because those products are not going to have any history of sales.
Okay, thank you, Thomas, Priscilla, and Eduardo. Round of applause for ASOS. Thank you very much.